So, the goal of last class and today's class is to explore one last topic in this last hour that I have with you, and that is about the power of randomization when it comes to algorithms. And so, the idea of flipping coins in an algorithm, how could it really help the algorithm? It's a very counterintuitive idea based on all the things we've talked about in the last 20 lectures, but it turns out that this idea of just making random choices helps you overcome many of the complexities or subtleties which you have to deal with when you work with deterministic algorithms. And we've already seen a few examples of that. So in terms of safety, having a strategy that the adversary doesn't even know. So they know he's going to flip some coins, but if you have a strategy that depends on the flipping of random coins, your adversary can't predict what you're going to do ahead of time, and then that could actually be a strategic advantage. So in this case, the match example was an example of how you can defeat an adversary by using sort of random coins and having a very simple strategy yourself. The second example was this fingerprinting idea. So we exploited this very deep number theoretic property to say essentially the same sort of thing, which is some adversary might have set up our situation where both of us have the same database or a different database and wants to convince us that we have the same database. It turns out that if you just pick a random prime, then with pretty good chance you're going to get the right answer. And if you do it twice, for example, by picking 2 or 3 primes, it's the probability that you make an incorrect assessment goes smaller very, very quickly. So this fingerprinting idea is sort of the same sort of principle, beating the adversary by choosing a random number which works with reasonable probability. And we can extend that idea and come up with an algorithm that's even more close to home, this idea of string matching, something that you probably do almost every day. You can do it rather efficiently with the very simple randomized algorithm, something that's maybe 20 lines of code to write versus the Knuth-Moyer-Pratt algorithm, which is much more subtle. I left last class, talking about this other example of a reliable communication problem. So the idea is you have a set of small nodes that you want. Each of the nodes wants to send a message to the server, but none of these, there's no coordination. These small devices aren't able to coordinate, and they're using a shared resource like the spectrum in the air. And if they both use it at the same time, then neither of them get their messages. So it's a real problem of the commons. But the same sort of problem happened before Wi-Fi, like in Boston, when everybody brought their cows to the Boston Commons, you have the same problem of making sure you don't destroy the commons by overgrazing it and so forth. And the insight to this problem is actually the real point that I want to show you here is that the tools of very basic probability analysis, along with this very interesting numeric fact, allow for very cool algorithms. This is just one example of a family of algorithms that relies on this particular principle. Okay, so the problem again, each node wants to figure out a simple protocol to make sure that it can get its message to the server. And as we talked about in last class, the simple algorithm is this. At each time step, you flip a coin with some probability that's related to the number of people that are involved. So here n is some upper bound, some reasonable upper bound on the number of nodes that are in your network. And you just flip a coin, and with probability 1 over n, you are the one that broadcasts at that time. Otherwise, you stay silent. And you do this for essentially n log n steps. And after that, with very high probability, you and everybody else that wanted to send a message will have succeeded. And here is the trick. I'm not going to go through the full analysis, but I'm going to give you the highlights of this because I want to cover a lot of cool stuff today. Okay, so here's the basic idea. Let's make this an event, a probability event. SIT is the probability, is the event that node I succeeds in sending its message at time t. So what is the probability? So this is a 1, for example, if the event is successful, and a 0 if it's a failure. If I fails at time t, it's a 0. If it succeeds, it's a 1. What is the probability of this event? what has to happen for node I to succeed at a given time?
And everyone else has to not.
Exactly. So another way of saying that is that it had to flip a heads. Right? And heads occurs with probability 1 over n. And everybody else had to flip a tails, right? So everybody else, they had to flip a tails, which happens with 1 minus 1 over n. And everyone except I. So 1, 2, 3, 4, I, all the way up to I minus 1, and then I plus 1, I plus 2, all the way up to n. So n minus 1, all the other people had to basically flip a tails. So we all agree that this is the probability that some node succeeds, right? Very good. So how do we analyze this kind of crazy expression? I claim that this is roughly 1 over n times e, where e is that magic 2.718, etc., etc. 7818. And this is one of the very cool basic facts in all of these type of randomized algorithms, and a lot of analysis in for randomized algorithms in general, and cryptography. And this is where this comes from. So this function right here, 1 minus 1 over n to the n, it's roughly 1 over e. And you can sort of do this by, of course, graphing this type of thing. And if you don't believe in graphs, which you shouldn't, I've shown this by graph for the first few hundred numbers. But if you actually want to prove it, what would you use? Everybody did this their freshman year, or they passed out of it. If you ever wonder what was most valuable from your first year, some APMA class where you learned about Taylor expansions, or the chain rule, that there are many ways to show this type of thing. I'm not going to do it here, but it comes back to a basic calculus type of ideas that you've done already in your previous class. This is the high level ideas to remember this type of equality. So once you know that fact, then you can analyze this, because this is going to be roughly 1 over e, and then 1 times n is roughly that. Okay? And so in particular, what you want to say is that your probability of success is at least 1 over en. And in fact, you can show that it's actually not that high. It's 1 over 2n is an upper bound on the success probability. So you succeed somewhere between this. And the core idea behind this randomized algorithm, and you should also take this as life advice, which is that, you might fail with some reasonable probability. Like this basically saying you have a 1% chance of succeeding at this type of thing. And you could, of course, look at the glass as half empty or half full. So as half empty, you'll be sort of despondent to say that, well, a 1% success probability is very low in life. But again, think about it. You're here at UVA, and that was certainly the success, the probability from, when you were born to coming here was certainly less than 1%. Okay, so you've already you've done many things in your life that have already, show that succeeding with probability 1%, you've already surpassed that. So if you're pessimistic, you'd think, 1% chance, I will never try. If you're optimist, all you have to think is that if I succeed with 1%, all I got to do is try a few hundred times. So if you try a few hundred times, in fact, you'll succeed with overwhelming probability. Okay? And that's the core of this, that's the idea behind this algorithm. Because, so if you denote the success probability as this right here, now we want to analyze what's the probability that everyone succeeds. Okay? Because that's what we eventually want to talk about in society, is how much, how many times you have to try for every node to succeed in this particular game. And so the way you do that is this, again, probability type of analysis, where you say, well, now let's look at this is the probability. Yeah. So FIT is the probability that I fails at times, not just time t, but times 1, 2, 3, all the way up to t. So FIT is the probability that I fail on the first t times that I try this, okay? And you can sort of say that, well, for me to fail at time 1, at time 2, at time 3, etc., that means that I failed at time 1, at time 2, at time 3, etc. It's an and of all of these type of operations. Right? And again, ands of probabilities of independent events you can multiply together. Okay, so this type of thing is also going to succumb to the same sort of analysis where this right here is basically 1 minus 1 over n roughly, right? It's going to be 1 over 2n because that was our upper bound on the success probability. And now the probability of all of these events is essentially to the t. Okay? So the question is, how many times do you have to try before you actually succeed? Okay? And what it says is that using the same fact that we just had, right? If t is roughly big enough, okay, you can analyze your probability of failing to be roughly n to the minus c. Okay? So if you make c like 3, for example, then your probability of failing, if you have, let's say, 1,000 nodes, could be less than 1 in a billion. So if you try roughly a few 400, 500 times, then the probability that you always fail is going to be less than a billion. And as we saw in the other day, the chance that you're 20 and you become 21 is already 0.1%, okay? Or the chance that you don't do that is already 0.1%. So a billion is a reasonable odd to take in life. Does everybody understand? We just used the same fact here to say that if you try hard enough, then in fact the probability that you always fail is going to be very low. Right? And we can put all of these things together by what's called a union bound. What is the probability now that every single node is going to fail after that many times? You use a union bound, and again, you get this idea that if by union bound, the probability that everybody fails is also going to be low if you pick your parameters correctly. So I've skipped a lot of the technical details, but I really wanted to convey the very high-level idea, which is this 1 minus 1 over n to the t idea. Even if you only succeed with some small probability, 1%, if you try enough times, then you'll eventually succeed. And that's the basis for this type of algorithm. And in fact, there's a closer example of this with the median algorithm. If you remember from the very first 4 lectures of class this year, we talked about this median finding, or the ith statistic. If you wanted to find the ith element in a given array that's not sorted, if you want to find the person that's ranked 17th in this class by their grade, for example, or by their age, then we talked about an algorithm, and it was kind of a complicated algorithm. It was a really sort of elegant way of doing divide and conquer. Thank you. What did we do? So the idea is we picked an element in the middle, and we partitioned across that element. So everybody that was smaller is on this side, everybody that's larger is on that side, and then we recursively solved the problem either on the left or right half, depending on what position we were looking at. The problem we encountered was what? What if you pick a bad partition? In fact, we were so concerned about this idea of picking a bad partition the first time and then doing it again and picking another bad partition and then doing it again and picking another third transition, and in fact getting into an n squared algorithm in this situation. We were so worried about it that what we did is we concocted an elaborate scheme whereby we divide the list, we pick the median of this, we create a sublist, we recursively find the median of this sublist, and that also called partition and so forth. There was this elaborate tango type of recursion between selection and partition. And you can imagine it not so easy to code this, even though conceptually you understand recursion and you think it's a very cool idea. So the randomized algorithm approach to this is in fact our original strategy. So if you want to pick a random partition, if you want to partition, don't use this tango. Just pick a random element. Okay? And the idea is the same idea we had in this node communication idea, which is, okay, as long as we pick some element in this orange zone, right? So let's make this orange zone essentially so the orange zone is roughly the middle 3/4 of the array. So if you pick something over here, let's call it a loss. You lost that round. But if you pick something in the orange zone, let's call it a win. Okay, because you've at least reduced the problem by at least 1/4 when you've done something like that, when you pick something in that range, right? So that's essentially the trick. What's the probability that when you just randomly pick, you get something in the orange zone? 3/4, right? So on expectation, how many times do you have to pick an element before you get to the orange zone? 4/3. Okay? So that means on expectation, you should expect to have to do this twice at every step of your partition before you actually get something in the orange zone. Once you get something to the orange zone, then you've gone to the next level. Okay? That's the same principle that we used before. Here you have a pretty good chance of getting something in the orange zone, so you might as well try a few times. Even if you had only a 2% chance of picking something in the orange zone, still, by our previous analysis, then that means you should just do that 100 times. Okay? And with good chance you'd be in that zone. Question? Very good question. So, if I would have had time, I would show you the formalism for how to argue this type of thing. How do you talk about the complexity? It's the same measure we've always been using. So what is the expected running time? So instead of the running time, in a deterministic algorithm, it's always going to, worst case analysis, you're always going to do this well. In a probabilistic algorithm, you can say, well, what is the expected running time of this algorithm? You can also do analysis of saying, well, if I run for just this much time, okay, I don't want to do an expected thing, because right, I could expect to be a millionaire, but then I could also become very poor, right? So if I play that, everybody know this St. Peter's paradox thing, right? Which is you go to the gambling casino and you put a $1 bet, okay? And if you lose, then you make a $2 bet. And if you lose that, you make a $4 bet. And if you lose that, you make an $8 bet. And if you lose that, you make a $16 bet. Eventually, however many losses occur, eventually you're going to win. At time I, you're going to win 2 to the I dollars. And so everything you've done before, you've lost 2 to the I minus 1, right? 1 plus 2 plus 4 plus 8, etc. Right? So this is a very good strategy because it guarantees you're going to win $1 at least, right? And then once you have a way to win $1, you might as well just continue your whole life doing this, right? You just make $1 every time. Okay? And why stop at $1? Call it $1,000. So every time you play, you win 1,000, right? What's the problem with this? The expected outcome is that you get $1,000, right? But with high variance, you lose, like the guy, you know, like all of these investment bankers in London, the big whale, and for example, you lose like, you know, $16 billion for your company, right? So in fact, that's the only principle if you want to become a, you know, hedge fund or an investment banker, a sort of gambler of other people's money. This is essentially the only trick you need to know, which is on expectation you're going to win, so you're going to be wealthy in life. But the point is, so there are 2 ways. You can talk about the expected running time for getting correct, which is one analysis, or a more conservative analysis. You can say, if I run for this much time, what's the probability I fail? And let's make that probability. We only consider probabilities for failure that are like, let's say, 1 in a billion, or, some very small number, like some small polynomial, right? So that's a good question. How do you analyze this algorithm? I'm going to give you the very broad framework. So if you miss some of these steps, don't worry too much. If you're interested, at least you'll get something out of this. But I want to get to what I really love about, this, the whole goal of this class was for me to share my enthusiasm. And there's cryptographic algorithms, which I want to talk to you about today. So the analysis here is as follows. You're going to look at phases of this algorithm. At each phase, essentially, you want to argue that the size of the input is less than 3/4 to the j, right? So at phase 1, the size times n. So phase j is when the size of the arrays that you're considering are smaller than this. And now what you're going to do is say, how much time do I spend in phase 1, how much time do I spend in phase 2, and how much time do I spend in phase 3, etc. The sum of all of that is going to be how much time I spend in the entire algorithm. Okay? And that's all you got to analyze. So how much time do you expect to spend in this particular phase? And that goes exactly by what you think it's going to be. Okay? So essentially you're going to spend this many operations. You're going to spend this much time, right? This is the number of iterations you have to do in phase j. And this is the amount of work that you're going to do in phase j, because your input size is this much in phase j. Okay, that's the expected amount of work that you're going to do in phase j. And now you use this very cool fact called linearity of expectations. Another very key idea from probability analysis that should be familiar. And that is that the expectation of the sum of these two things is just the sum of their expectations. And so you can say, how much time am I going to spend when in kindergarten? Well, the expected time is 1 year, but sometimes it's more. So maybe across America it's going to be 1.04, because some of the people do it again, right? And so again, expected time in first grade is going to be 1 point, right? And then expected time in 9th grade, when you get to there, actually it's probably higher, like 1.4, 1.5. Now you're doing like, trigonometry and math and so forth. Sometimes you have to redo 9th grade and 10th grade and 11th grade, etc., right? And so the sum of the time of your education in elementary, in grade school, for example, is expected to be 12, but possibly like a little bit more. So maybe like 12.4, right? Same idea here. So the expected running time in this case is just going to be still beta n, just like the deterministic algorithm. But what was the advantage? What did we gain from this? Simplify. Yes, very simple implementation. You can imagine it in your head. You just pick a random spot, right, and try to do the simple quicksort partition type of thing. Right? Again, a 10 or 12-line implementation versus a 40-line implementation. Okay. So I come to this following question of private communication where randomization is critical, and I'll show you this in several steps. So private communication, one is Alice, one is Bob. Alice wants to send this message to Bob, but Eve is eavesdropping, and we want to try to do this in a way that Eve doesn't learn what that message is. And of course, describing what it means not to learn what that message is takes a whole lecture, takes a lot of framework to get a good idea, but this is the gist. And this isn't a problem that just we've manufactured, right? All of these people have had this problem, and in fact, if you do it poorly, like this woman right here, the Queen of England before Elizabeth I, Mary Queen of Scots, she used crypto, she had a bad algorithm, bad randomness. In fact, she didn't have randomness, and so her code was broken, and she perished. Okay, and other people also use these type of encryption schemes. What do I want to talk about? So, at this point, I'm sure you're familiar with these type of simple schemes, like for example, a substitution cipher. Here, what you do is you have some alphabet, right? And your key is some permutation over the alphabet. Okay? So for example, A is going to map to J, B is going to map to C, etc. You do some permutation on the letters, and then to encrypt, you just apply this permutation everywhere. This has a very big key space, lots of possible keys. So it's not the case that you can just guess a key and hope that it's right and decode your message. So the regime of randomized algorithms where you just pick and hope that it works out doesn't work in this case when the key space is too big. But there is, of course, a fatal flaw to this encryption scheme. What is that? Frequency analysis, right? People look at this type of thing, and you can notice that certain letters like this, yeah, so you know that the English language has, we already talked about in Huffman coding how there's a different frequency, each letter has a unique different frequency. It's not all uniform, and so you can do that sort of analysis on this type of thing. There's another problem with this encryption scheme that has been resolved recently in the last, let's say, 35 years. In fact, this scheme has been the same, it's been the same for like 2,500 years, and then in around 1978, 80, there was a breakthrough. Can everybody guess what that idea is? No, I mean, you can, instead of 26, you can pick like 256. The idea that I want to get to is that in all prior encryption schemes, you had the property that the sender and the receiver needed to exchange a key beforehand. Okay? Can you imagine if this was the state of the art today, what the world would be like? Do you think you could buy something on Amazon if Jeff Bezos had to come to each of one of you and say, here's a key, here's a key. If you want to buy something, use this one. Oh, here's a key. If you want to buy something, buy another key, right? You think they could have scaled that way? If to buy something on Jeff's site, you had to personally meet with him and get a key, or maybe not him, but one of the 10,000 people that work for him, it just wouldn't work. Our whole digital economy relies on the fact that we can encrypt messages in a way that doesn't require this one-to-one exchange of keys. Okay? That's called the public key cryptography. Okay? And one of the first schemes that started that idea was this RSA paper, 1978. Okay? And so what I want to talk about is public key encryption. And here, the main idea is as follows. Okay, how do you buy something on Amazon today? When you do SSL, what do you do? Exactly. So what we're actually using is TLS, which is a more sophisticated protocol, but let's boil it down to the essence like we do with everything in this class. Amazon has what's called a public key. It's posted it somewhere on the internet. There's nothing secret about that aspect of it. And I can check it. I can either call them or I could go through some other mechanism like a certificate authority and have someone else verify that that's the right key. All I got to do to send an encrypted message to Amazon is to know this public key. So I can encrypt a message to Amazon using Amazon's public key. That's going to produce a ciphertext. Now, the only person to decrypt this message needs to have Amazon's secret key. Okay? So, classically, the notion of encryption was really a box where two people had exactly the same key. In order to lock the box, you did like this, and in order to open the box, you had to have the exact same key, which wouldn't work today. We couldn't buy stuff online, couldn't do anything really cool. The public key idea is that the key that locks it can be different than the key that opens it. Okay, so what are the big ideas that we need in order to implement them? In fact, I'm going to tell you that I think you only need 4 ideas. Okay? You have to know the idea of modular exponentiation. So there are only 4 ideas to understand the basic idea of RSA encryption. So, and we're going to go through them. In fact, modular exponentiation, there was a homework problem. Divide and conquer, you figured out a way to compute a to the x mod p efficiently. In fact, that's very critical for this algorithm right here, but we've already covered something like that. We have, in fact, greatest common divisors is also a divide and conquer algorithm. And I believe I gave it as a homework in one of these, maybe, all right? But it's also a divide and conquer algorithm. So both of these are divide and conquer. Picking large primes is an example where we need to use randomness. The best way, the most efficient way we know to do that is using random coins to do that. And finally, this is just a fact from math, which pulls all of this together and makes it actually work. But it's a rather simple thing, which I could describe in a few minutes. So let's go through this at a very high level. So modular exponentiation. The problem, yeah, question? Euler's, this is a TOTIENT. We can just say Euler's theorem. Okay. Thank you for that. So, modular exponentiation. The idea is that you want to compute this value right here. Okay? And imagine imagine this x is like 100 bits long, or 1,000 bits. Okay? So for example, it's very easy to compute a to the 12, right? You can do that in just 12 operations using the simple thing. But what if you needed to compute a to the number just goes on and on. Okay? Thankfully, you guys all came up with a very clever way to do this, okay? And it was a divide and conquer where you essentially, you do what's called repeated squaring. So this formulation is the iterative version of a divide and conquer. So in order to compute a to the x, you basically compute a to the x over 2. And then you square it. Okay? Everybody remember this? And this mod n part of it just means that all of your operations you do mod n. And you're familiar with mod n. So mod 13 means take your result and divide by 13 and just keep the remainder. And what's nice about mod n is that you know that your answers will never go beyond n. So you can allocate the amount of space that you need, however big n is, ahead of time, and then just do your computations. You'll never need more space than that. Even though this number, if this is a very large exponent, this number could be enormous. In fact, the number could be so large as to take more particles than there are in the universe to write. But still, you can compute the number mod n as long as n is a small thing. Right? So that's a first idea. Everybody comfortable with modular exponentiation? If I give you, let's say, 17 squared mod 11, what would it be? Who said it? Let's say 17 squared was 389. Then what would it be? Or is it 289? Yeah? 3. Okay, great. Okay, so 3 is the answer. Okay, so aside from the mathematical aspect, everybody conceptually understands this idea of mod n. Very good. First idea, check mark. Second idea, this is an algorithm that Euclid came up with. It's the greatest common divisor of two numbers. So in your head, what is the greatest common divisor of 35 and 14? Fantastic. And how did you do it? You probably recognized that this was the case, and so you did a prime factorization of these two numbers and then took their intersection, right? So although this is one way to do it, it doesn't work for very large numbers because in particular it requires you to factor these numbers. What Euclid figured out was that there's actually a way to sieve out the greatest common divisor without the factorization. And it is also a very cool divide and conquer algorithm. Okay, so yeah, the point is, for example, solving a problem like this, you couldn't factor these numbers in your head, but if I gave you, you couldn't factor these numbers in 5 minutes, but if I gave you 5 minutes and this algorithm, the extended Euclid algorithm, basically, don't be freaked out by that. I heard that holy shit comment, but the basic idea is when you're given, when you want to find the greatest common divisor of A and B, that's actually equal to the greatest common divisor of B and A mod B. Amazing twist. You can prove this in a paragraph, and you can analyze this algorithm. It runs in log n time because it's one of those divide and conquers, because every step, one number becomes smaller than the other number. In every 2 steps, essentially the numbers divide by a factor of 2. Question? N is the number of bits. Sorry, N is essentially the size of A. Okay? You can call this A. So, in other words, the running time is the number of bits in the biggest number. Okay? So, what's remarkable about this simple algorithm is not only does it let you compute the GCDs of things, but it also, so Euclid came up with his GCD algorithm, and someone extended it. When you extend it, you can actually also compute values x and y such that ax plus by is equal to the GCD of these values. Okay, so for example, it's best to see this as an example, right? So surprisingly, you know that the GCD of 35 and 14 is 7, but remarkably, you can always find numbers that when you multiply by A and B, get you that GCD. Yeah, so for example, in this case, what is the GCD of 13 and 73? What's the GCD of 13 and 73? 1, right? 13 is a prime, 73 is a prime. So, good. Now, what's cool is that you can actually find numbers There was a time when I think I might have been able to do this, but today let's see, can I figure it out? 5, 350, 350. Ah. There we go. Okay, so $365, and this right here is amazing, huh? This is a 2,300-year-old fact, okay, that you can compute the GCDs quickly, and in fact, there's an algorithm for computing the numbers such that you can add multiples of these two in order to compute this, to get this GCD. This will be an important fact in this RSA algorithm. So all I wanted to point out is that what you've learned, divide and conquer, gave you modular exponentiation and gave you this Euclid's extended Euclid algorithm for computing this. 2 of the 4 things that were needed to basically power the internet economy. And you know them. Okay. So the third thing, how to pick very large prime numbers. So here we go. Here's a very large prime number, and for cryptography, I think your intuition leads you to think that you probably need very large prime numbers, or at least big numbers in general, in order to do any crypto. So how do we generate large prime numbers? Small prime numbers are easy. I give you like 72 and you're like, no, it's no. 72 I can factor 2 times 36, so forget about it. 73, divide by 1, no. Divide by 2, no, that's 37.2, whatever, 36.5. Divide by 3, no, that's also a fraction. Divide by 4, well, it's never going to be divisible by, if it's not divisible by 2, it's not going to be divisible by. So, and you can go up and say, at some point you get to 8. 8 times 8 is 64. 9 times 9 is 81, and so you don't need to consider any numbers beyond square root, essentially. So that's called the sieve. So if you want to check whether a number is prime, you can just try all of the factors up to its square root. And if none of those are integers, then you know the number is prime. What's the problem with that algorithm? How long does it take? If I have an n-bit number, I have to check up to square root, right? I have to check up to n over 2 bits. So it takes roughly 2 to the n over 2 time. Okay? Not good, not good. Wouldn't work, because for crypto you need like 1,000-bit keys, right? So to check whether a 1,000-bit number is prime by using the sieve, I would have to do 2 to the 500 amount of computation. Okay? So not a good idea. Thankfully, Java helps us out here. You can pick a prime number just by doing this. Okay? A 2-line algorithm. But of course, this will pick a 1,500-bit prime with reasonably high probability. The probability of failure is 2 to the minus 80. So the point here is that the third concept, this idea of picking large primes, the best way we know how to do it is to use randomness in order to do it. And this algorithm is called the Rabin-Miller algorithm. It's a little bit too complicated to go through in this class, but I'll tell you 2 other places you'll be able to get it. Next year, I'm going to teach a course on privacy-enhancing technologies, and we'll go over this thing. But if you can't take it next year, next fall, so either next spring with me or next fall with Mohammed, our new crypto professor, he's going to teach an undergraduate course on theory of cryptography, and we'll certainly cover this algorithm. So the point is the algorithm is actually, again, just like random algorithms, very simple. It's a 4-line algorithm. You're going to, aside from base cases, for t, where t here was 80, you're going to pick some random number and check whether that number is in this crazy set. Okay? And this crazy set essentially amounts to checking whether a to the n minus 1 is equal to 1 or not. Okay? This fact right here is related to this Euler function, which we're going to talk about. But all I want to express to you with this simple algorithm is that you can pick random numbers using a very simple test. The analysis of this test is kind of subtle and requires some number theory, but the algorithm itself is something that any one of you could implement, again, in less than 20 lines of code. I'll tell you the story. For a long time, we were wondering whether there was a way to check primality without random coins, and whether we could do that in polynomial time. And so the only way we knew was this Rabin-Miller algorithm from, again, the 1970s. During my grad school tenure, while I was in grad school, these 3 people from India, AKS, 2 of them, the A and the S, were undergraduate students. Very smart advisor, though. Those 3 figured out a deterministic way of checking for primality. It was like basically the best result of 2002 in theoretical computer science. So it solved the major open problem, can you do this deterministically? But guess what? It was way, way slower. Just like the median finding algorithm, although so median finding algorithm, deterministic and the randomized are roughly the same complexity, but in practice the randomized thing is much faster. In this case, This algorithm runs in sort of n cubed time. Sort of you have to do, certain number of multiplications essentially. And it's rather efficient. For 1,000-bit numbers, you can do it very quickly. This AKS algorithm was something like n to the 6th time. So it was well beyond practical. But still, it resolved an open question. So again, the best way we know to do this, although now we figured out a way to do it without random coins, is to use random coins in a simple way. All right. So, final idea is this Euler TOTIENT function. Okay? And this function, it's called phi of n. I'm sure all of you know your Greek letters better than I do. Phi of n is the number of integral, number of it's the number of positive integers that are smaller and relatively prime to n. So for example, phi of 7, let's figure out what a phi of 7 is going to be. Is 1 relatively prime to n at 7? Yes, because GCD of 7 and 1 is 1. So in fact, 1 is relatively prime. So is 2. What about 3? Okay, good. You'll sort of see that, of course, in this case, since 7 is prime, the TOTIENT function of any prime number is going to be p minus 1. Right? Because every number that's smaller is going to be relatively prime. That's the definition of a prime number. How does this happen? How does it work when it's not a prime number? Okay? Let's take a look at 15. So very quickly, let's go through this. 1, yes or no? Everybody in unison. 3. No, because GCD of 16 and 15 is 3, right? So it's not relatively prime. Yes, yes, no, no, yes, no, yes. So 1, 2, 3, 4, 5, 6. 7. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. Should be 8. Okay? So phi of 15 is equal to 8. 15 is equal to 3 times 5, right? That's its prime factorization. So it turns out that this is also equal to okay? So the point being that so phi of a prime is going to be p minus 1, and phi of n is going to be phi of all of its prime factors. Okay? Why do we care about this phi of n function? Because it actually has a very cool number theory property, and this is called Euler's theorem. So if a and n are relatively prime, there's this very cool property, which is that a to the phi of n is 1 mod n. This is why RSA works. And we had to wait until the 1700s in order to figure this out. Euclid already had the modular exponentiation and the greatest common divisor. This came in the 1700s, and then the randomized primality testing came in the 1970s. Those were all the pieces that were needed for this public key encryption idea. Now, let's see. Can I give you a few examples? So, why is this true? There's a kind of cool idea that if you had a little bit of number theory, you can get this idea. And I'll give it to you as a very short little vignette. So, take all the numbers basically in that set. If we look at this phi of n right here and just consider, if we consider all of the numbers that are circled, a cool way of writing that set is like this. Z star n. That's a cool way of writing that set. And the basic idea is you write all the numbers in that set in a circle like this, and right next to it you write that number times A, mod n. Okay? And the very next step is you argue all of these numbers and all of these numbers are distinct and in fact the same. Unfortunately, So, write all the numbers that you have in a circle and multiply them together, and then write all of these numbers in a circle and write those together. And you need this one other fact, which is that this set forms a multiplicative group. But if that follows, then essentially you can divide out. You can write this as essentially product of and then divide both sides by this and get A is equal to 1 is equal to. Okay, so in fact the proof is slightly more complicated than I anticipated, but the big idea is you write both numbers, multiply them all together, and divide. And I've skipped a few steps because I want to get to this slide. So textbook RSA, the algorithm that puts all of these four pieces together. Here's how you do it. So you pick two prime numbers, P and Q. And these are roughly, let's say, 1000-bit numbers. And now you set n to be P times Q. How would you multiply these numbers? We learned an algorithm for this. Divide and conquer, Karatsuba, exactly. Then you compute phi of n, which is equal to P minus 1 times Q minus 1. Okay? And finally, so these are the steps. You pick those prime numbers, you multiply them, and you compute phi of n, just by subtracting one and multiplying them again. And then you pick some e. Typically, you can use something like e is, at first, e could be some small prime number, like 17, but that turns out that that's not such a good choice. So typically, it's something like something like this, which I believe is a prime number. But it's a small number. It's only like 16-bit. It's a 16-bit prime number. So typically you pick that to be some prime, and then since it's prime, the GCD with phi of n is very, very likely to be, in fact, almost is guaranteed to be 1. And then you can use the Euclid algorithm to basically, since the GCD is 1, you know that there has to be a number E times D such that the answer is going to be 1 mod phi of n, right? Because Euclid tells us that there's some number like this that is equal to 1. Right? So these are the 5 steps that you need in order to pick an encryption key. And now let me show you how RSA actually encrypts a message. Very cool. It's M to the E. And decryption modular exponentiation again. Right, so this textbook RSA algorithm, all it does is 1 exponentiation to encrypt. Notice that all you need is the public key here, which is E. And all you need here was the secret key, which is D. And of course, if you could, and of course you also need N in both cases. Okay? So the public key is going to be the pair N comma E, and the secret key is going to be N comma D. Notice, if I just give you N and E, why is it hard to compute D? In fact, very few people know why it's hard. But we know that if you could factor N, you can certainly do it. If I could factor N, given N, if I could factor it, then I can basically compute phi of N, and then I can compute D using Euclid. The hard part of that solution is factoring N. We don't know yet how to do that. There might be some other clever way of computing D given just N and E that doesn't involve factoring. Like Euclid found a clever way of finding GCD without factoring. Maybe there's a clever way. Everybody that has considered cryptography, has read even a simple paper about it, has tried to solve that problem. So at least 1 million people, I can guess, have thought about that problem. And those are smart, 1 million smart people. And nobody's really figured out how to do it. So, of course, it's a great challenge. If you could figure out how to get D without, then the first thing you can do is break, first thing you can do is become a billionaire, okay? And then, of course, you'd be a famous academic. So there's a lot of glory involved in breaking RSA. Why does it work? So imagine computing the decryption of the encryption of some message. Okay? That's going to, so the encryption of some message is going to be M to the E, right? And then the decryption of that is going to be and here is why it works. Because we know that ED is equal to 1 mod phi of n, we know that this is equal to some number k times phi of n plus 1 mod n. And now, I've used 3 of those pieces that I talked about. How do I use the 4th to analyze this last step? In particular, what is this right here? Look up there. A to the phi of n is equal to 1 mod n. So what is this right here? this is like m to the phi of n to the k times n mod n. Exactly. So this is basically 1 times m mod n. Does everybody see that? This part, by Euler's theorem, this is just 1 to the k, which is also 1. And since we have that extra 1 right here, we pull that m down. Putting these 4 pieces together, that's what Revest, Shamir, and Edelman did. And the story goes, Revest and Shamir had, kept on suggesting, different formulas, different ways to try to do this, and Edelman would break every single one of these things that they came up with. Finally, they came up with this, and Edelman couldn't break it. They thought about it even more than that, and then they suggested that this is a secure public key encryption. This is a trapdoor permutation, which they then suggested to be used as an encryption. But there's one fatal flaw in this encryption scheme. Textbook RSA doesn't work. Why?
Because we put in the end of in mod
n mod n is such a big number, and your message only has to be, you can cut your message up into short chunks. The reason this doesn't work goes back to the very first slide of this class. The same reason that Mary, Queen of Scots, and all of these other people, they also perished. Why? They didn't have any randomization in their scheme. In fact, in the longer version of this lecture, I wish I would have finished, we would have gone through an example of what this RSA scheme is. But what I want to point out, another anecdote here, is the Battle of Midway, in which, the Battle of Midway was turning point in World War II. Here was the critical fact of this. Japanese fleet was going to attack some island in the South Pacific there, and they didn't know which one it was. So Japanese had an encryption scheme where they're encrypting the name of the island that they were attacking, but it was a deterministic encryption scheme. So every time they said this island's name, they used the same particular code for that thing. That's what allows frequency analysis. When I encrypt the, THE over here, and I encrypt it again later in the message, if I don't have a randomized encryption algorithm, then both of these instances will be exactly the same code. So in this Japanese Battle of Midway, the Midway, the island, was used twice. And these two commanders that I just pointed out in the previous slide, they were able to trick the Japanese command into saying that name twice in 2 different messages. Here's how it happened. The commanders sent a fake message from Midway saying, hey, we're in Midway here, we're out of water. Water doesn't work. They waited a few days, and then 2 days later, they intercepted a Japanese transmission that said, Island AF. So first they intercepted a message, we're attacking Island AF, and then 3 days later, they see a message that says, Island AF does not have water, good time to attack. So because they were using a deterministic encryption scheme, the encryption of Midway was the same in these 2 messages, and therefore the US fleet was able to deduce that the surprise attack was at Midway, and so then they did all like this and the red arrows and the Battle of Midway. Okay? So what's the point of this story is that every encryption scheme needs to be secure, needs to have random coins involved, meaning if the encryption algorithm isn't using randomness, it's broken. And so there was one standard PKS 1.5 which said, to encrypt a message M, instead of just M to the E, like it was instead of this right here, actually do it like this. Pick some random R that's like 8 bytes, and then put all these bytes right here and then encrypt the message. That scheme was a hack, and it sort of worked, but there was an attack against this one as well, much more sophisticated attack. And in fact, you needed to do things much more carefully, and in fact, this is very close to the right way to do it. In fact, it's the right way to do it, but as you can see, it's sort of more complicated. Next semester, we'll talk about this algorithm and so forth. The point that I want to make is that the very first step of that randomized algorithm is to pick random coins. Okay, so that is why four or five different ways why encryption is good. I want to spend the next 3 minutes giving a short summary and an idea of what the final exam is going to be like. So, right, what was the theme of this course? Small problems are easy to solve. Solve big ones by turning big problems into small ones, right? I think we've done that pretty well, pretty effectively in several topics: divide and conquer, dynamic algorithms, greedy algorithms, graph algorithms. There was a big section here. I had planned 5 lectures on NP completeness, and you just wonder where the time went. So I know that Nathan gave you 1 lecture on that. I'm really hoping that you can complete your education by either using MOOCs or by taking 3102 and getting the theory of NP completeness. It's very important. It relies on this algorithmic idea of reduction. We didn't get to cover it, but we did cover about 50 problems. So these are the blue problems. On NP completeness, we didn't get to talk about, vertex cover, 3-coloring subset sum, set cover, independent set. But we did get to cover a lot of topics that were not on there. For example, a guest lecture on GPUs, guest lecture on this cryptographic descent problem, and several of these things. Now, what will the final cover? It's going to be like a homework. It's going to be 4 problems. I agree with a question that someone posed on Piazza that I dropped the ball. I didn't give you a review session. I tried to do too much this week. Wasn't able to get it all basically together because of various constraints. So I will hand out the exam sometime next week. Like I was thinking Monday, I'll give you a physical copy that you can pick up from the office. You can start the exam whenever you want, so you can study for as long as you want. I assure you that it should take you 1 or 2 days to finish this exam. The problems have been scaled down in complexity so that you should be able to solve these things. They will cover basically, essentially these topics right here in the boot. Okay, so I really want you to know about these type of things. Okay? I really want you to know about these type of graph algorithms. I think we've had the most practice about these type of things. So the idea is it'll be due next Friday. It'll be due next Friday, and you can pick it up anytime on Monday. So it should be flexible with your schedule and so forth. I will try my best to get you a review, either by the TAs or by me. I'm leaving town on Sunday, so I'll try to do it on Friday or Saturday. But someone will give a review section over all of these particular materials. I've handed out all of those solution sets. Please make sure you pick them up and look them over. What were our goals? I really hope that we've created a good learning experience for you. I hope that you have some enthusiasm for algorithms and that sometime in your future life you'll remember this and solve some problem. And certainly, I know that I have satisfied this goal, for sure, because I've really enjoyed we've gone slower than we have in previous classes, but I've really enjoyed it. Part of it is because you were so interactive and asking really great questions. So good luck with whatever you do in the future. Truly, I've taught this several times, and this is the best instance of this class because I know you put a lot of work into it and you were very proactive in class. So congratulations and good luck.
I just wanted to say thank you. It was a fantastic semester.
Great. Yes. And please finish these cookies.